So everyone's not paying attention. We have a new neighbor up there.
Hello, my name is Declan O'Brien. I'm a PhD student. My advisor is Shinlin Lee at University of Colorado Boulder, and I'll be moderating the Q&A session for this plenary session.
And my name is Alexandra Wold. I'm also a PhD student at CU Boulder, working with Dr. Bob Marshall. Dr. Xiaojia Zhang received her BS in space physics in 2008 from Peking University, China. Then she went to UCLA to pursue a PhD in space physics. After graduating from UCLA in 2014, Dr. Zhang worked at UCLA for a few years and then joined the Department of Physics at University of Texas at Dallas as an associate professor in August 2022. Dr. Zhang's research focuses on wave-particle interactions in the Earth's and Jovian magnetosphere, energetic particle precipitation, and the related magnetosphere-ionosphere coupling. In recent years, Dr. Zhang also endeavors to mature space instrumentation and mission concepts for CubeSats and smallsats. Please help us introduce our speaker.
Yeah, thank you, Alexandra, for the introduction, my background, and thank you for being here, in such an early morning session, and also thank you for inviting me here to give this tutorial talk on inner magnetosphere. It is really a pleasure for me to deliver such a talk to our early career scientists and the students. But when I got this invitation, I started to look at really carefully about the tutorial talks from previous speakers that was uploaded online, even more so than when I was sitting there. So that's why I realized, all the basics in the wave-particle interaction or in the inner magnetosphere have already been well covered by each of our previous tutorial speakers. So what I will be focusing on today will be try to introduce some of my personal understanding on this topic, and especially focusing on the recent advances in the past decade also on this topic. And also, given the time constraint, of course, I cannot cover every study in the past decade. So it's my privilege to just pick those my personal favorites. So please bear with me if these are not your personal favorites, okay? So as the title says, I will be talking about the current status and perspective of wave-particle interaction in the inner magnetosphere. Before that, I would like to acknowledge all my co-authors as listed here, and also the Alphen, Summers, and Valenpros team for providing the data that enabled all the great works included in this presentation. So this is the what I will try to cover in today's presentation. And so let's quickly start from a brief introduction. As we all know, it's not showing up. Thank you. So as a quick introduction, as we all know, the Earth's magnetosphere is actually occupied by a wide variety or wide range of charged particles, and also all sorts of plasma waves that are generated within different regions. As you can see from this famous illustration of plasma waves in the inner magnetosphere, we see these typical wave-thermal waves that are predominantly seen from the midnight towards the dawn sector. and these magnetosonic waves mainly observed from noon to post-noon sector, and also the IMAG waves also predominantly seen in this dusk sector. And what's not shown here is those ULF waves that are more often observed or generated along the flanks of this magnetosphere. So speaking of wave-particle interaction, of course, there are two possible ways, right, between the waves and particles. Firstly, how do the waves affect the particle dynamics? And secondly, how do the particles affect the wave growth in return? And in this presentation, I'll be focusing mainly on the first part, and specifically talking about the wave-particle interaction for electron dynamics. And then the first natural question, actually, after we know what we are going to talk about, is why do we care about wave-particle interaction? So basically, it means the wave-particle interaction means energy, or to be more precise, is important channel for energy flow, either from one population to another or from one region to another region. So as we know, the ultimate energy input for our Earth's magnetosphere is the solar wind. So as the solar wind energy comes into the magnetosphere and then transported into the magnetotail, part of the energy are further transported towards the inner magnetosphere, but part of it was returned or released back to the interplanetary space. And for those energies that are transported or end up into the inner magnetosphere, which is the topic of our interest today, about 40% of them are actually dissipated through particle precipitation. And the wave-particle interaction basically plays a dominant role in driving this continuous particle precipitation, as we talk about that dictating the energy flow from the magnetosphere towards the ionosphere. Then how does this happen? How does this wave-particle interaction happen in the inner magnetosphere? So let's step back a little bit and then look at firstly the particle dynamics or particle motion in the magnetosphere. So this famous sketch just illustrates three types of particle motion in Earth's inner magnetosphere or in the more dipolarized magnetic field region. So it dictates, as shown here, it basically includes a gyration around the magnetic field and also a bounce motion between the two mirror points at the two hemispheres, finally a drift motion around the Earth. As you can see, like illustrated here are about electrons, which is the topic of interest in this presentation. And corresponding to this, each of the periodic motion that we can reconstruct or define adiabatic invariance as listed here. And then, so this seems like a pretty nice picture of particle dynamics in the inner magnetosphere. But then how come, or how does the wave-particle interaction come into play into this nice picture? So basically, wave-particle interaction, what does it do is that it actually affects the particle motion in a way so that it destructs one or two of these adiabatic invariants. And this will happen under the so-called resonance conditions, to be more efficient. So first of all, we are talking about wave-particle interaction under this resonance condition. Then what does it mean by resonance, right? So in simple words, without having to introduce these equations to the right, the wave phase in resonance basically means the wave phase remains unchanged along the particle trajectory, so that the particles will always experience or encounter a constant wave field along their motion, so that this kind of constant wave field will continuously change the particle motion and then ultimately violating one or more these adiabatic invariants. And then what does it take? What does it take to have this wave-particle interaction? Sorry, to have this wave-particle resonance. So one basic requirement is that, of course, because we're talking about the phase between the waves and particle motion remain unchanged, right? So one natural requirement is that the wave frequency and the corresponding particle motion frequency should be comparable. So listed here are the typical frequency ranges of 3D particle motions in the magnetosphere. So as we can see, in order for cyclotron resonance to occur for the electrons, that we should expect those waves on the frequency range of hundreds of hertz to tens of kilohertz typically. So this dictates those Whistler mode or ECH waves that we observe in the magnetosphere. And similarly, in order for bounce resonance to occur, we see like this time we expected to have the waves with frequencies on a couple of hertz, right? So this basically means those magnetosonic or oblique emitting waves. And similarly, last for the drift resonance to occur, we would expect those waves that on the order of millihertz range, or those so-called ultra low frequency waves. And I didn't go into details of these 3 resonances, but I do include a couple of examples from previous studies about each of these resonances, just for your reference offline. But we will not talk about this in detail here. So yeah, so these are the 3 kinds of references resonances that we can expect in the Earth's inner magnetosphere. Then where are we now? So let's first review our current status in this wave particle interaction studies. So as we know, or as we heard about a lot in the earlier sessions of this week, that the basics of studying wave particle interactions is the so-called quasi-linear theory. And what it means, it basically means that for low wave amplitude, the particle motion can be treated or can be approximated as unperturbed when we look at the particle momentum change, or when we look at the particle energy and pitch angle changes. And so I've listed here, sorry that this doesn't show up properly, as I listed here that the detailed derivation of this quasi-linear theory, but we will now try to go through them one by one here, and then just for your reference later on if you need it. And so if you would do trust it, right? So let's directly jump into the second from the last line here. So it means here like the perturbation in electron moments is directly or linearly proportional to the wave field or to the wave amplitude as shown here. And because of this sinusoidal form of the wave field, when we average it over these wave phases at resonance, it basically will give us a zero mean change in the particle momentum perturbation. But like if you were to look at it, the square of this term, it basically will give us a non-zero variance. And it happens that this variance in particle momentum actually correspond to the so-called diffusion rates as we use to quantify the wave particle interaction in this quasi-linear theory. So as expected that we see these diffusion rates are proportional to the wave intensity or the square of the wave amplitude. So all of these are consistently with what we have been understanding from the past, right? So after adapting this generalized diffusion rates and also adapting it for different plasma wave modes, this quasi-linear diffusion equation, or the so-called Fokker-Planck equation, become widely adopted or widely used in studying the wave particle interaction. And so shown here to the right is one such example of applying this quasi-linear theory or diffusion theory in the inner magnetosphere dynamics. So we can see like what's shown here is the observed and modeled electron phase space density profile as a function of time, right? I mean, at different times. As we can see, that the simulated electron phase space density actually reproduces well the observed electron phase space density in a way that it shows a consistent or successful application of this quasi-linear theory in the long-term electron dynamics. Of course, that there have been a lot of similar studies like this, applying those quasi-linear theory into the electron dynamics or proton dynamics. So it basically all of them shows that the quasi-linear theory was able to reproduce those long-term dynamics as we observe in the magnetosphere or inner magnetosphere. And then the question is, shall we stop here and the problem is solved? So shall we just call it a day? So just because like our field is largely guided by the observations or spacecraft, right? So let's look at what does the data show or how does the data lead us towards. So of course, we are talking about wave particle interaction today, but it doesn't hurt to just step back a little bit to look at all the data or all the observations in the Earth's magnetosphere. So I just quickly summarize all these spacecraft observations in different areas of our space-time. So as we know, here, that Explorer 1 basically marks the beginning of our space physics or space era, at least in US. So that the famous valence radiation belts was discovered just using data from a simple Geiger counter. So that's the initial stage of our study. And the following 6 decades also just saw a lot of breakthroughs whenever that we have new measurements or new instruments available, especially say in the 1960s with the instrument of electrostatic analyzer, we started finally to be able to measure those particle energy spectra at different regions of the magnetosphere so that we are able to finally reconstruct the topology of the magnetosphere in different regions. And also for our wave particle interaction, a seminar study is, a golden time is in the 1970s, where like we have a lot of coordinate measurements between this low Earth orbit satellite and those equatorial satellites, and also between the space and the ground. So all of these are telling us that the origin of those diffuse aurora that we often see on the ground, in the camera data are actually driven by some processes in our magnetosphere. So that's also the first time when this pitch angle scattering by plasma waves or wave particle interaction was first introduced to explain the aurora phenomenon that we see on the ground. So afterwards, the following years basically see, I will not go through them one by one, relax, okay? So the following years basically see a quick growth of this field from a tiny seed, of a single wave particle, single type of wave particle interaction to quickly grow into a big tree of radiation belt science with different branches of different plasma wave interaction with the particles, with different types of electron dynamics on different time scales and at different regions of interest. So that's whenever I look at this history, I just feel like interesting. So let me share with you some of my personal thoughts after looking at the brief history of our field. So because of course the point is not to listing the facts, right? Is what matters more is like what we can gain from looking at this history. So first of all, that because of the higher temporal resolution and because of the improved technology or capability in telemetry, that we see that the yearly data return per mission quickly rises up with time. So what it basically means that you can see right now we are getting 1 year of data return that is comparable to 10 to the 4th years when we just started the measurements in space. So with such a large data set becoming available on a routine basis, So it becomes popular that we start to use more and more those CubeSats and small sats in our space exploration, just because of their shorter turnaround times, and also because of this much lower cost, so that it basically can provide more easily more observations in more points, right? And also more opportunities to advance the space technology to validate our scientific models. And as we come into this era of big data, one personal thought I have here is like, we will need to find a way to unify the data analysis process so that, later on that our analysis can be streamlined as the data becoming available to us on a shorter and shorter time scale. But again, this is a long-term effort and also just my personal thoughts. And then, so let's get back to our wave-particle interaction, okay? And to see like what kind of new information we can get from this brief history that we just talked about. So back to the wave-particle interaction, what we see from the previous chart is, of course, we have more and more observations that covers a wider spatial range in our inner magnetosphere with higher temporal or angular resolution data, right, in particles, and covering a wider energy range. And specifically, or in particular, in the valence probes era, we start to have this simultaneous energetic particle and wave measurements routinely available to us. And it was at that time, people more and more clearly realize that the quasi-linear theory we just talked about cannot fully explain all the particle dynamics, especially over shorter time scales. And then that's when a lot more studies are focused on nonlinear wave-particle interactions. One side note about this is like, if you think about it, the theory about the nonlinear wave-particle interaction has already been developed back to 70s actually, but then it was rarely reconstructed or revisited until early 2000. And then it was not until the valence probes era that people started to very intensively study this nonlinear wave-particle interaction. So basically I just think like it's a good example to illustrate how data and theory go hand in hand in our field, right? And so, okay, back to our main storyline here. In addition to a lot more studies focusing on nonlinear wave-particle interaction, a lot more efforts have been devoted to introducing or to quantify this wave-particle interaction by different wave modes or by more plasma wave modes, so that they can use it to explain those unresolved questions in the inner magnetosphere. So let's look at what's the nonlinear wave-particle interaction. So as we talk about, or as we introduced earlier, the applicability of quasi-linear theory in wave-particle interactions basically requires a wake wave amplitude, but then how wake it should be, right? So quantitatively, this, again, sorry, the proportional symbol was not properly showed up, not proportional, much smaller, right? So basically from the theories, it can be derived that the wake wave amplitude basically means two things. Either the wave spectra should be broad enough so that the wave at each single frequency cannot trap the particles for a long time, so as to introduce those, efficient electron acceleration in the nonlinear wave-particle interaction, or the background magnetic field gradient should be strong enough to be dominating over the wave force, right? So that the electron detrapping can occur more easily. So basically, this boils down to the two criteria as two conditions as listed here, but hopefully you can see it better in the PDF version. So then that's just a theory, right? So as we talk about how does the data look like in our field, this is the one of the guiding line for our work, right? So as shown here is a typical example or spectra of Whistler mode waves in the inner magnetosphere. As we can see, like at a particular time, we see the waves are actually highly coherent, directly violating the first condition that the waves should be broad enough, right? And then, how about the second one? So the lower diagram here shows the probability under which that the wave intensity or amplitude is strong enough to overcome the background magnetic field inhomogeneity. So in short, this means like under which conditions that the second condition is violated. So as we can see, like in the statistical work, about 30% of the time, the wave amplitude will be large enough to violate the second condition. So this seems to indicate, right, the nonlinear wave-particle interaction are expected in our inner magnetosphere or radiation belt science. But then where are we? I mean, what are the recent works on this? So later, right now in this section, I will talk about our recent progresses in these two aspects, focusing on those newer results in the last decade. So first of all, in this work by Zhang et al., it was showing that these bursts of coarse waves are highly correlated with this bursts of intense electron fluxes in the energy range of tens of keV. And you see like this correlation is almost in a one-to-one fashion. And also one thing to note is that these electron distributions exhibit those so-called butterfly distribution. And in the test particle simulation, the authors are able to show that this kind of electron bursts or enhanced electron fluxes were caused by the nonlinear cyclotron trapping by the electrons, nonlinear cyclotron trapping of electrons by this observed coarse waves, so that you see a simultaneous increase of pitch angle and energy, and so that to result in this kind of butterfly distribution was also observed in the Valen probe data. So in a way that this shows or this supports the fact that this nonlinear cyclotron phase trapping can explain those fast electron acceleration and the formation of butterfly distributions under this cyclotron resonance. In another study by Apigadov, I probably didn't pronounce his name correctly, sorry, that Valen probes observed this oblique Whistler waves as shown here. And in the meantime, the particle data shows enhanced field-aligned electron fluxes in this roughly in this energy range. And what does the open circles mean here? They just show the expected energy range of the electrons when they escape from those so-called nonlinear, Landau trapping. So basically it shows that the expected energy range of these electrons after the nonlinear Landau acceleration agrees well with the observe the electron flux enhancement, both in this energy spectra and also in the line plots down below here. So this indicates that this kind of good agreement basically indicates the this nonlinear Landau phase trapping can explain those fast electron acceleration at low pitch angles. But of course, that we are talking about those highly oblique Whistler mode waves here, just to be clarified, just to be clear, sorry. And then later with the availability of alpha and CubeSat data, which basically are the direct measurements of energetic electron precipitation at LEO orbit. When the loss cone opens up, you can directly measure those precipitating electrons, right? So what's shown here with this data set available, more and more studies start to look at or to validate the previous theories about particle precipitation. And shown here is one example of alpha measurements when it traverses the different regions of Earth's magnetosphere. So here in this region, we're talking about the outer radiation belt, and we see these two strong bursts, strong but short bursts of electron precipitation, as both shown in the precipitating electron energy spectra, and also this precipitating versus perpendicular electron flux ratio. So in the meantime, that because this happens in the September 2019, so when we still have the Valence probes monitoring the equatorial wave environment. So in the meantime, the Valence probes, Valence probe A actually captured those intense field-aligned Weissenmol waves as shown to the right here. And so this basically indicates the potentially important role of this field-aligned coarse waves in driving this kind of intense precipitation, but then how to validate it, right? So that's how Chen et al. Used his model of combining ray tracing and test particle simulations to simulate or to model this precipitated electron energy spectra during this conjunction event. So shown here is the model, the precipitating electron energy spectra, perpendicular electron energy spectra, and the ratio between these two. So we can see, say from this flux ratio plot, it actually reproduces well the observed energetic electron precipitation that we see at LEO, in the sense that, you know, the energy range expands from tens of keV from bottom to up to about 1 MeV in the case consistently with the observation here. And also, if you were to compare the detailed flux ratio, they are actually quite close in energy, in each of the energy channels here. So basically what it means like is the nonlinear cyclotron scattering can explain those intense but short time scale electron precipitation that we often observe at LEO. And another example of the alpha measurements was shown here when it, again, in the outer radiation belt region, starts to capture those intense precipitation of electrons with energies from 50 keV up to about 400 keV. So looking at this precipitating to particle to perpendicular energy flux ratio, we even see that this ratio can exceed 1. So which cannot be possible for this cosilinear theory, if you are familiar with it. So that's why we call this kind of phenomenon the loss cone overfilling. And it happens in the meantime, or not happens, right? It's a typical example. So in the meantime that we have summits that captures those oblique, highly oblique Weissenmol waves in the conjugate equator, which I didn't show here. But then with the wave information, what we do is that we model those expected particle energy spectra driven by the observed oblique coarse waves. So shown here is our observation and the model results in a similar format, showing the pitch angle distribution with the fluxes at each pitch angle normalized to those at 90 degrees. And we can see, comparing these two, our model was able to reproduce to a great extent, at least, this observed electron distribution, and also which dictates this loss cone overfilling, basically, with increased flux even within the loss cone. So this kind of case study or modeling in this kind of conjunction event basically indicates that the nonlinear Landau phase trapping can explain the loss cone overfilling that we sometimes observe at LEO. And then with this kind of nonlinear with particle effects showing up in our data, the next question is like, how can we incorporate them into our radiation belt models, right? So the way to do it is like, we can use this kind of generalized diffusion equation. Then all we need to do is to quantify these terms that are responsible for nonlinear wave particle interaction, or those so-called phase bunching and phase trapping effects. But this is not an easier task actually, because this interaction or these terms for nonlinear trapping and phase bunching cannot be analytically derived in most of the cases, in all the cases. So that's why most often people adopt this test particle simulation to model the particle dynamics after a single or multiple wave particle interactions in this nonlinear regime. And then, I mean, based on this, some approximations can be made to basically reduce the computational cost that comes with the test particle simulation. And one such approach is the so-called green function approach. We don't need to talk about the detailed equation here, but just like what it did is by using the series of test particle simulation under a certain wave property, basically it quantifies the probability, the electron pitch angle and energy change in the presence of the waves, and then incorporate it into this kind of green function, and then further adopted it into this generalized diffusion equation to model the long-term electron dynamics. And down below here in the bottom shows the example evolution of the electron phase space density directly from this green function approach. And another or an alternative approach is proposed by Chen et al. In early 2020s. So basically it combines those retracing model and test particle simulations in a way that this is, I would think that this is more of a state-of-the-art model because instead of relying on this prescribed wave field, it actually directly traces the wave propagation and including the wave damping by those thermal and superthermal particles, and the wave propagation effect and wave divergence in our dipolar magnetic field. So basically after this retracing, you can reconstruct the wave distributions, right, along a particular field line, and then test particle simulations can be conducted at each of these points wherever you need it, and then to simulate or to model those nonlinear wave particle interactions. And then one thing to note is that this kind of sophisticated models is more suitable for simulating those short time scale events, of course, especially those so-called microbursts, which are the intense and short precipitation of energetic electrons in the radiation belt. So it's shown here that this model was able to nicely reproduce this microburst caused either by the ducted Western waves, Western mode waves, or non-ducted Western mode waves. Yeah, so that's a second type of model. And the last model is the so-called mapping technique. So this model is actually similar to the green function one that we just talked about 2 slides ago. But the difference being that instead of using the test particle simulation to numerically derive the particle energy and the pitch angle variation, the probability of trapping and also the particle energy and the pitch angle variation were derived analytically, of course, under the some reasonable approximation of the wave field. And then by averaging this particle dynamics, right, over an example of observed the distribution of wave characteristics, they were able to reproduce or model the long-term dynamics of the electrons in the presence of this nonlinear wave particle interaction. That's pretty much all the models that was used in the so far for the nonlinear wave particle interaction. But one thing to note for this mapping technique is like, of course, compared to the green function approach, it is less precise in a way that it involves some sort of approximation or assumption to the wave field. But then it significantly reduces the computational cost so that it can be easily adopted for long-term dynamics, for simulating long-term dynamics. And also it can be readily incorporated into MHD fields, say, to model those even longer time scale electron dynamics. Yeah, so as I said, like in the beginning, in addition to the nonlinear wave-particle interaction, there have been increasing efforts in introducing different wave modes or different physics in the wave-particle interaction. So the first kind of wave mode is the so-called kinetic alpha waves, which are this kind of broadband electromagnetic waves that was basically brought into our outer radiation belt by those particle injections. And then if you look at it, that the frequency of these kinetic alpha waves actually are quite low, so it cannot directly cyclotron resonance with the electrons, right? So that's why a series of work by Chaston et al. Quantified this so-called bounce drift resonance between the electrons and these kinetic alpha waves. Is actually quite a sophisticated interaction, but in a way that it also resolves, it also leads to almost a constant wave field along the particle trajectory. And then by quantifying looking at the wave spectra, we see that this is quite broadbanded, right? So as we talk about, this means that this probably fall into the quadilinear regime for the wave-particle interaction. So that's why in the series work, Chaston et al. Quantified the corresponding pitch angle and the radial diffusion rates from these kinetic alpha waves. But to be honest, this is mostly happen for the hundreds of keV electrons, as you can see here. But the overall contribution of kinetic alpha waves to our radiation belt dynamics has yet to be fully explored. Let's put it this way. And another kind of wave-particle interaction for the kinetic alpha waves and electrons is the so-called Doppler shifted Landau resonance. Yeah, such a long term, right? But like basically, it's the same thing, right? In the aftermath of electron injection or particle injection, it brings, this is K parallel, V parallel here. In the aftermath of particle injection, it also brings into the inner magnetosphere the large gradient of background magnetic field, and which comes with, or which leads to increase the gradient drift of the electrons or particles in general, so as to put those Doppler shifted wave frequency to be in Landau resonance with these radiation belt electrons in the energy range of tens of keV to a few hundreds of keV. So as this recent study by Shen et al. Shows that the pitch angle diffusion by kinetic alpha waves in this Doppler shifted Landau resonance, it actually shows quite significant pitch angle scattering rate for this whole energy range from tens of keV to a few hundreds of keV. And if we were to compare the resulted energetic electron precipitation spectra of flux plotted here in red, and compare it with the direct observation at LEO. This is a conjunction event between MMS and alpha. So you see like these two agrees quite well, to some extent, of course, indicating that this pitch angle scattering and the related energetic particle precipitation from these kinetic alpha waves can be potentially important for the electron precipitation at this energetic energy range. Another type of new physics is the cyclotron resonance with so-called time domain structures. So what time domain structures basically are this kind of broadband, again, by electrostatic emissions or structures that can be observed in the magnetosphere. And to the right here, we show the waveform data for one type of TDS structure, which we call the electron hole, which they call the electron hole. And in the recent series of work by Vasco et al. And Shen et al., they started to quantify even I forgot to mention that, sorry, this is K parallel and V parallel again. And because of the drift velocity of this TDS structure, it can fall into this generalized cyclotron resonance with electrons. And in a recent work by Vasco and Shen et al., it was shown that the pitch angle diffusion rates by these time domain structures can be quite appreciable for the energy range of listed here below about 10 keV at least. Although that this is low energy part, but it actually corresponds to the diffuse electron precipitation. So that's why it was argued, it was claimed that the cyclotron resonance with these TDS structures can complement those wave particle interaction or pitch angle scattering by wave thermal waves and ECH waves in driving the diffuse aurora. And the last type of interaction I want to mention here is the nonlinear scattering of energetic electrons by IMAG waves. As we all know, a long-term open question in IMAG wave studies are the energy range of electrons that was precipitated by these IMAG waves. And so in a recent study by An et al., it was shown that the short wave packets or this limited wave periods within each wave envelope, right, as shown here, can very effectively expand the energy range of these precipitating particles. So as you can see, like compared to this long wave packets, it actually extends the lower end of the energy for the precipitating particles to about 300 or 400 keV, compared to the long wave packets where the lower energy boundary is about 600 or 700 keV. So it actually quite an effective expansion of the energy range. So, and also what's unique about this event is that, or the studies that they used this kind of conjunction event between alpha and MMS, I think. So that in the, at Leo orbit, alpha basically observed a consistent range of electron precipitation that from a couple of MeV down to about 400 keV. So in a way that quite consistent with their model results, and then indicating that this kind of nonlinear wave particle interaction by IMAG waves is a possible candidate to explain those sub-MeV electron precipitation that often accompany this IMAG wave-driven precipitation above the minimum resonant energy. I mean, basically above MeV range. So this is pretty much I wanted to cover for this presentation. But I suppose that most of you probably are already lost by this point. So no worries. So let me quickly summarize what we have talked about in this presentation. So let me try to see whether I can do this well. So before we talk about the test particle, wave particle interaction, let me tell you a story about a different field, the electromagnetism. So in the field of electromagnetism, it all starts from a simple, the first discovery of electricity by Franklin. So, and then later years that the field quickly grows as people start to describe the electric field and magnetic field and start to discover those electromagnetic induction, actually by Faraday. And then all of these inputs or development in this field was then summarized or unified in a sense into the great Maxwell's equation. So looking at this kind of development in the electromagnetism, so basically we can see a general trend of experimental physics or experimental science, right? So it starts from a simple discovery, and then progressively become more and more complicated as we have more inputs. And then eventually it becomes simplified again. So putting this, our wave particle interaction into the same storyline here. So basically our study or our field starts from the introduction of waves in order to explain this wave-driven aurora, right? And then with more and more observations, we start to gain more and more knowledge about wave particle interaction. And in the past decade, we even start to talk about all sorts of nonlinear wave particle interaction and introducing even more plasma waves into our models. And all of these are in this first stage here that we see a quick growth of the field. And then, of course, I'm happy to be able to contribute to this stage. But like hopefully in the audience, we have some young talent, you know, that someday can unify our field so that, you know, we have a model or two that can incorporate all sorts of wave particle interactions into our models. Yeah, so with that, I just wish you good luck and look forward to see this revolutionary moment of our field. And with that, thank you for your attention and happy to take any questions.
Awesome talk, Xiaojia. We have about 3 minutes for questions.
You'd be better off with an inflatable bag. That's what we did. We had an inflatable bag, wasn't tumbling, and then you can, everything's motorized and it pulls together and collapses, right? You suck it in.
Somebody
But
online.
all this jumping around and trying to, it's.
Somebody on the Zoom. Okay, thank you.
Really nice tutorial, Xiaojia. Congratulations. So in your tutorial, you demonstrate really nicely that nonlinear effects are important, at least in a short time scale. So could you briefly comment on how much difference do nonlinear effects make when we simulate the long-term electron dynamics compared to the quasi-linear theory?
Oh, yeah,
Thank
yeah,
you.
sure. Thank you for the question. Actually, I didn't have enough time to introduce detailed work about this nonlinear wave particle interaction. But in recent years, a serious work was devoted to studying the wave characteristics that affect this, not only the quasi-linear theory, but also the nonlinear wave particle interaction. So as far as I know, the most recent work or conclusion is that because of the short wave packets dominating over the wave waves, say, it basically lead to such kind of nonlinear wave particle interaction regime that falls in between this quasi-linear regime and also those idealized nonlinear regime with, you know, infinitely long sinusoidal wave. So in a word that in short, it basically means more or less close to diffusive regime, but like with diffusion rate or energization rate or scattering rate much faster than the quasi-linear theory at a given wave amplitude. Thank you.
Okay. Yes, Xiaojia, enjoying your talk. All those wave particle interactions can do a lot of things, right? So my question here probably more about the measurement. I know the Alphen worked wonderfully for years. Also, there's spin 3 seconds spin period.
Mm-hmm.
So my question is about this J parallel ratio, because you're spinning like 3 seconds, and then you have like particularly 1 MeV, the bounce period is like say less than 0.1 second. And so was that a possible like just a data sampling or aliasing? Just see when you're spinning 3 seconds, you measure like say in the local loss cone some flux, but then you spin the local trap population for another say 1 second, 2 seconds. During those time, could that be some aliasing cost that the ratio can be greater than 1 for particular high energy? Can you comment on that part?
Yeah, sure. That's really a good question from an expert on the CubeSat measurements, you know. So basically, yeah, you are right that basically this kind of resolution that we have at Alphen suffers for a lot from the time aliasing, because like over half spin, we can only resolve the full pitch angle spectra. That's on a time scale of 1.5 seconds. So if anything happens in a shorter time scale, we do have this problem. But for this particular event, as you can see, the trapped fluxes remains, I would say, quite constant. So that's why we sort of trust those long time scale measurements. And also for this event, we do check this. We did check the high resolution data I mean, those so-called spinning data, right? Spinning sector data on the time scale of 180 millisecond, and showed similarly thing that enhanced the precipitation within the loss cone. Yeah, so you are right that caution should be executed for when we look at the short time scale precipitation, but like hopefully the longer or higher resolution data can help us with this time aliasing issue. And also we do look forward to new data, right, from other CubeSats with higher temporal and angular resolution. Yeah.
All right, thank you so much, Xiaojia. I'm sure she'll be in the break if there are more questions, but to give time for our next speaker, we're going to now have the student moderators come up and introduce themselves and introduce the speaker.
Good morning, everyone. My name is Krishna Khanal, and I'm a PhD student at University of Alabama in Huntsville. I'm working on dayside magnetopause reconnection, more specifically looking at the spatial extent of reconnection X-line at dayside. I'm working under the supervision of Dr. Ying Zhu. I'll be moderating the Q&A session. Thank you.
And I'm Pauline Dredger, recently graduated from University of Texas at Arlington and soon moving to University of Michigan. And it is my great pleasure to introduce our next speaker. Dr. Joo Hwang has experience in a broad range of space physics topics, stretching from the magnetotail to the magnetosheath and down to the ionosphere. She received her Bachelor of Science degree from Korea University and her Master of Science from the Korea Advanced Institute of Science and Technology, before receiving her PhD in space plasma physics from Dartmouth College in 2006. She did a postdoc at CU Boulder's Laboratory for Atmospheric and Space Physics, where her work used both data analysis and simulations. After this, she moved to the Goddard Earth Sciences and Technology Center at University of Maryland, where she worked on pre-launch studies in support of the MMS mission. Dr. Hwang is now a staff scientist at the Southwest Research Institute, and her work focuses on the microphysics of the ion and electron diffusion regions in dayside and magnetotail reconnection. She's also investigated global phenomena occurring in Earth's magnetospheres, such as Kelvin-Helmholtz waves and flow vortices at the dayside magnetopause. She is the first author of more than 30 papers and co-author on many more. Please give a warm welcome to Dr. Joo Hwang.
While we wait, in case she had to step out for a second, Ian Cohen, are you in here right now? By any chance? Oh, okay. Since Ian's not here, is there anyone else from the advocacy panel today who would like to? Yes. Oh, I just thought I'd use we could use this time for someone to advertise the lunch event. Thanks, Lindsay.
Cool. Hello, everyone. My name is Lindsay Goodwin. I'm going to slowly work to the front so people can see my face. But yeah, I'm Lindsay Goodwin. I'm assistant professor at NGIT, which is one institute that's part of the Helio Coalition, which is a a group of institutions that are working together to advocate for heliophysics, both in terms of politically, like so talking to Congress and fun stuff like that, but also just kind of branding like who we are and like making it so that like even people outside of this field understand who we are and what we do. Because if you go up to a person on the street and say, oh, I do heliophysics, what is that? People won't necessarily know what that is. And also just trying to like normalize in the world saying words like plasma and fun stuff like that. There was a ton of really good white papers about it that's really cool. But yeah, so we're going to be having a session today starting at 12:50, not 2:50, that's not lunchtime, 12:50 going to 1:30, I believe. Yeah. But yeah, 1:20, thank you. But yeah, so please pop by, ask questions. If you want to get involved, we would love to have you involved. But yeah, so that's as much time as I can fill right now. Thank you.
Thank you so much, Lindsay, for that very impromptu announcement. Just making sure Joo's not here yet. All right, we thought that maybe we could do the focus group announcements now instead of at the end. So if you're a focus group leader, please feel free to come up to the front like we usually do at the end of the plenary to announce your session for today.
So our focus group, Radiation Battle Focus Group, we will be having our last standalone session today, right after this session. So we will be focusing on a discussion around the machine learning usage in radiation battle studies. And also we have a few more early career scientist talks. So please show up to support our community. Thank you.
Hi, everyone. The MPEC in time-space asymmetry, MPEC and GIC focus groups will have a joint session at Pacific A after this session. And after lunch, we will have a panel discussion with MPEC, Meso, and DIP focus groups. And later on, we will have a third session with the MPEC self-consistent inner magnetosphere modeling and the machine learning focus groups, again at Pacific A. Thank you.
Hello, good morning, everyone. I'm Christian Ferradas, and we will have a session after lunch for the self-consistent inner magnetosphere modeling focus group. And then, as Doug just mentioned, we'll have a joint session with the precipitation group and the machine learning group in the second afternoon session. And you can please look at the schedule for the rooms. I don't have it right now, but thank you very much.
Lynn, go ahead.
Oh, okay. Yes. So I was planning to come down and say this in person, but I was trying to get some last minute work done. Anyways, I'm Lynn Wilson. I hope you all know me. If you don't, you can always bug me at the session today. We have 2 shock sessions today. So if you're unsure about what session to go to, shocks are probably the best thing you can choose because they're like the buy one get 500 free type of option, because everything we care about and love happens at shocks: wave particle interactions, particle energization, reconnection, turbulence, everything, kinetic theory, all the stuff is cool. So, yeah, so if you are curious, come over to I think we're in the coast room, or the one that's not near where you got, not where the plenary stuff is. We have 2 sessions, one in the 10:30 and one at the 1:30. So thanks.
Great news. We've located the next speaker. She'll be here in about 10 minutes. So I think if we'll ask her not to go, we'll ask her to shorten it so that we still end punctually, but feel free to chat or go take a potty break, but please come back by what time is it now? Sorry, I'm a mom, so sometimes my language reflects that. Come back by 9:20, please. All right, everyone, if you could please make your way to your seats. Settle down. I know we just had a wonderful, quick little break. You already had heard the beautiful introduction from the student moderators for our next speaker. So now let us give a warm welcome to Joo Hwang.
Okay, hello everyone. I'm very sorry to give you unexpected break. Yeah. So maybe it's not enough. I think maybe a few days are not enough to get accustomed to California time. Okay, so hello everyone. So my name is Joo Hwang. Excuse me. So thank you for giving me a chance to talk about two of the most interesting topics today. And so I'm going to talk about the flank side and the day side dynamics of the Earth's magnetic pulse, focusing on the multi-scale properties of flux transfer event, FTEs, and the Kelvin-Helmholtz, K8s, vortices, and waves and vortices. So this is my outline. So after introducing the magnetic reconnection and the KH, Kelvin-Helmholtz instability, and NASA's MMS mission, I will briefly talk about the shock and the magnetic shift region, which may help understanding the related contexts about FTEs and KH waves. And then I will walk you through the two topics, FTEs and KH waves, focusing on their generation and multi-scale structures and the global impacts. And then I'll summarize my talk. Okay, so let me start with two hypotheses that you might be familiar with. So over like 60 years ago, Dungy and Oxford Hines proposed two different models of the solar wind and the magnetosphere interaction. So as you see in the left figure, in the Dungy cycle is Dungy model is best presented in the new midnight plane, including the two neutral points or X lines here and here, across which there's the magnetic field changes rapidly oppositely, triggering reconnection. Then the reconnected magnetic flux tubes is transported over the pole to the night side, where the magnetic tail reconnection pushes it back into the inner sphere and outward. So the Dungy model is powered by the large magnetic shear. And on the other hand, Oxford and Hines emphasized the velocity shear, which result in the quasi-viscous interaction along the flanks magnetic pulse. So this is best represented in the equatorial plane, as you see in this cut. So since then, the two most important physical processes in the solar wind and magnetosphere coupling is reconnection and the Kelvin-Helmholtz instability, KHI. So the current score is this model wins. So the Dungeon model has been supported predominantly by simulations and observations, but we still have an unsolved question. Says the viscous interaction becomes more important as you move further down the tail, since the KH vortices grow in size. Then can this model significantly affect the solar wind transport across lengths? So this is one of the unsolved questions, and it could be your take-home question. Okay, now, so start with the magnetopause. The Earth's magnetopause is characterized by the existence of a magnetic shear, which triggers reconnection, and the velocity shear, which triggers KH instability, vortices, and waves. And here the magnetosphere is hot and tenuous, and magnetoschist is cold and dense. So there is asymmetry in the density and temperature, which also triggers ray-light tail instability or the lower hybrid drift instabilities. So today, I'm going to focus on the first two, which provide the generation mechanisms for FTEs and KH waves. Okay, so I'm going to talk about some textbook stuff for reconnection. So plasmas are magnetized, that is the proton in magnetic field. And magnetic field rapidly changes. The field lines breaks and reconnected, and plasmas gets demagnetized. And after they merge, the magnetic tension flings the plasmas to the left and right. And during this process, the energy stored in the magnetic field is converted to the particle energy. That is, Joule dissipation occurs. So this is called inflow and outflow, or exhaust, or this is called the X line. So so as you see this movie, the reconnection is initiated by the electrons in this small region called the electron diffusion region, where electrons are demagnetized. And then reconnection entails the ions in the ion diffusion region, where ions are demagnetized. And then the reconnection ultimately propagates its effect to the macroscopic scales, such as the auroral and the global magnetospheric convection, as we saw in the beginning. So here, maybe I can. So red is the electrons, and the white is ions. So electrons was first reading the reconnection, and then reconnection entails ions. Okay. In the electron diffusion region, the electron microphysics is important. And in the ion diffusion region IDR, the whole physics due to the electron ion decoupling is important. I think I missed one slide, but yes. And the MHD governs the macroscopic scales. So as you see, the different scales are dominated by different physics. So this is why we care about the multiscalarity. Then how small the EDR and IDR? Here the EDR is on the order of the electron inertial length, DE, or the electron gyro radius, such as a few DE, for the width of the EDR. And the IDR is on the order of the ion inertial length, DI, or the ion gyro radius. Okay, so now we change gear to KH instability. So the KHI or KH waves are generated along the Earth's magnetopause, across which there is a significant velocity shear between the fast anti-sonoid magnetoschist flow and almost stagnant or slightly anti-sonoid magnetoschist flow. And these KH waves can develop into the large scale KH vortices. And later, we will discuss the solar wind entry driven by KHI. Like reconnection, KHI also has the multi-scale nature. So the trains of KH vortices have a scale size of the 10th RE or 1,000 of DI. A single vortex is on the order of RE, but you see the small structures along the KH boundaries that are generated by secondary instabilities. So you see in this movie about the KH vortices, so this turbulence cascade that are generated by the secondary tearing mode in this movie is also generate multiple scales, and which is a characteristic of KH instability. So we will actually come back this movie or this feature later. Now we move on to the MMS mission. So the goal of MMS is to resolve the 3D structure and dynamics of the multi-scale X lines all the way down to the electron scales. So to do this, you need high time resolution measurements and a small spacecraft separation down to electron scales. So MMS consists of 4 identical spacecraft. Then why 4 spacecraft? This is to measure the 3D physical quantities, such as 3D velocities. That requires 4 points measurements. And the MMS 4 spacecraft, the tetrahedral configuration enables calculations of gradient, curl, divergent, or curl. But the spacecraft separation should be down to the DE size to detect the EDR. So the EDR, the DE electron inertial length is about 5 kilometer in the dayside magnetopause and around 30 kilometer in the magnetic current sheet. So and DI, the ion inertial length, is about 40 times of these numbers. So in geospace, all the relevant scales are well separated to be measurable by in situ. For example, however, on the other hand, the DE in solar corona is around 1 meter. So we cannot place 2 spacecraft 1 meter apart. So our home planet provided the best laboratory to access all multi-scale physics during the reconnection and KHI at work. Okay, so let me move on this one first. So the first and foremost achievement by MMS is the detection of EDR. So it's the high time resolution measurement, in particular, the 30 millisecond cadence of electron distribution functions revealed the crescent-shaped distribution in the EDR. So in this EDR, you see, excuse me, the B changes, I lost my cursor, so B changes, and the E field and VE cross B shows some deviation. So if the electrons follow the field, they should be actually agree, but it shows a deviation. And at this point, you see the large J dot E prime, so Joule dissipation. So this is there is possibility that this is an EDR. And around here, as you just mentioned, you see the non-gyrotropic electrons. In this cut of the electron distribution function, the B field is out of plane direction. And so if the electrons are fully magnetized, you expect the gyrotropic distribution. When you see here, crescent-shaped non-gyrotropic distribution. I just wanted to show this movie a little bit. So yes, it's just to rotate the 3D distributions. Okay, so this is observed, obtained during the 30 millisecond. Then why is the crescent? So here, so this is the reconnection plane. If you look at this side, but first let me introduce the LMN coordinate. The L is along the nominal magnetic field, and N is along the magnetic field, the current is in normal direction, and M completes the orthogonal coordinates. So if you look at this side, so cuts of M and M here. So the electrons in this region gyrate according to this B field, and they cross the current sheet, now be changed, and the gyration gets changed as well. So the velocity 1, 2, 3, 4 corresponding to this crescent shape in this distribution. Let me actually skip those and one of the another notable finding from MMS is the evaluation of the relevant contributions of each term in the generalized Ohm's law. So again, the small space separation enabled the old calculations of these divergent and J, which is a curve B. So, and the result is the electron pressure term, pressure gradient term, is actually important in the EDR here, but the electron inertial term is non-legalizable as well in the EDR. And if you subtract the sum of these two from the left-hand side term, the residue indicates the anomalous resistivity. It might be possible, might be partly driven by waves in this event. Okay. So now we move on to the shock and magnetoshifts. So, so as you know, the angle between the IMF and the bow shock, the normal, is greater than 45 degrees. We call the quasi perpendicular shock. And the angle is less than 45 degrees, it's the quasi-parallel shock. And the upstream of the quasi-parallel shock is called the forward shock. And the electrons and the particles are backstreamed from the reflected from the bow shock. So if you see only those backstreaming electrons, for only electrons, it's the electron forward shock. And if you see also the backstreaming ions, it's the ion forward shock. And then these backstreaming electrons, backstream populations, or here ions, yeah, backstreaming ions and the original solar wind can generate waves via such as two-stream instabilities. They can generate waves, and these wave fluctuations propagate across the shock. So the downstream magnetoshifts is more turbulent in the parallel shock side than the perpendicular, the quasi-perpendicular shock side. So prior to MMS, the ion scale reconnection current sheet was observed in the turbulent metal sheets. But after MMS, well, actually MMS observed the reconnection everywhere, including foreshock and both side shock transition regions and both side downstream magnetic sheets. Although there is a little preference to the parallel, quasi-parallel shock side. And also one of the most important findings for MMS is the electron-only reconnection observed in the turbulent magnetic sheets. So here MMS3 testing here, so observed the B reverser and J.E prime enhancement, so Joule dissipation and corresponding ion outflow here. But there's no, electron outflow here, but there's no ion outflow. So they called this is electron only reconnection. And this electron only reconnection might be the initial phase of a regular ion reconnection. So this is the active current area, research area these days. Then how about the cage vortex? Yes, MMS also observed the full electron-only vortex. So here you see the electron flow reversers and the flow vector rotations, but there is no such feature is observed in the ion velocity. And so we found that the electron cage instability condition was satisfied across each the velocity layer. And we are now comparing this observation with the peak simulations, such as J.E prime and also the generalized Ohm's law, etc. So this is a work in progress. Okay, so now we finally move on to FTEs. So the very first observation of FTEs are made by Alfig and Russell and Alfig, and they identified the bipolar BN signature with the magnetic strength enhancements. And they interpreted those as localized flux ropes passing by the spacecraft, which generating positive BN and negative BN. So since then, much of the FT study is focused on the various generation mechanisms. So the original, Russell and Alping model invokes the transient burst of dayside reconnection, and the resulting FTs is a elbow-shaped flux ropes with one end connecting to the magnetosphere and the other end connecting either the northern magnetosphere, northern ionosphere, or the southern ionosphere. And there, the emissive extent is narrow. And the single, also the temporal modulation of the reconnection rate during continuous reconnection can generate a single X-line FTs. So here the enhanced the thermal pressure in the exhaust region caused the event to burst outward. So there's only one X-line here. And in the multiple X-line reconnect the FTs, the edges, two edges of an FT is anchored at two separate X-lines here and here. So in this case, the ion jets from each X-line compress, they converge toward the FT center and compress the FT. And in both cases, show can extend over many RE azimuthally. Let me skip all the details of these three models. So those three different models give rise to different magnetic topology, but they are all based on the reconnection. They are all reconnection-based models. On the other hand, the MHD, the resistivity MHD, MHD simulation just showed the formation of the subsolar FTEs, which is the helical magnetic field lines that are rolled up by vortices, as you see the flow vector here. So the size is almost the RE or more than RE size. And then MMS observed an ion scale FTE, also driven by flow shear. So in this event, the flux rho or FTE is embedded within the electron velocity shear layer. So this FTE is most likely generated by the electron, the KH instability. So let me skip this. We will actually talk about this under the KHI. Okay, so now we take a look at the multi-scale structures and interaction of FTEs. So this MMS observations shows that a series of actually 5, a series of the flux rhos observed in the exhaust region of the reconnection, so which is called the secondary islands. So what's interesting in this event is that these 5 actually, for somehow it's missing here. So these 5 flux rhos are bounded by the initial and later X lines, and we found that the 2 X lines drifted apart, and then the current sheet between the 2 X lines gets thinned to be unstable to the tearing mode, generating those the multiple flux ropes. So this event was simulated by compared by the simulation, and the result is shows very good agreement with the data. And these FTEs are predicted to grow to Earth size within 10 minutes. And the major source is the continuous reconnection at adjacent X lines. However, the coalescence of 2 flux ropes or erosion can decrease the island's magnetic content. So the first observation of the coalescence of 2 flux ropes is shown here. So you see the very sharp PN change, which is due to the dissipation via reconnection occurring at the interface of the 2 flux ropes. And then we move on to the interlinked flux tubes. So interlinked flux tubes are predicted maybe more than 30 years ago, but lacked observation evidence, which was provided by MMS. So when the IMF has a significant BY component, and the ion jet, the reconnection occurs here and here, and the ion jets compress the current sheet formed in the interface of the 2 interlinked flux tubes. And this compression facilitates reconnection. So it's all observed by MMS. And this localized reconnection results in the evaluation of a magnetic topology of interlinked flux tubes, either becoming simplified or more complex. In both cases, the one flux tube is connected to the magnetosheath, complementary magnetosheath, where you see the needle high energy electron population, and the other flux tube is connected to both hemispheres, where you see the 90-degree pitch angle electrons of high energy. So there is a very rapid change across the center of this FT signature. Okay. So this is the last part of the last slide for FTEs. So the global impacts, one of the global impact FTs are shown in this event, where the NMS observed a series of the FTs, so 1, 2, 3, 4, 5, 6 here, and the all sky image in the ionosphere. In the all sky image observed the forward moving auroral forms, and these multiple forward moving auroral forms show the one-to-one correspondence with these FTEs. And the decay, after the decay, the forward moving auroral forms, you see the occurrence of enhanced density blobs in the polar region, which is called the polar cap patches. It moves tailward, so like forward, and duskward, as observed by radar as well. So this event shows the complete sequence of solar wind, dayside magnetopause, and ionosphere coupling with the FTEs as an important ingredient. Now we move to the KHI. So let's start with the KH instability condition. So this condition basically tells you the velocity shear across the shear layer is greater than the hybrid alpha speed KHI occurs. So you may note that the K vector, K vector, perpendicular to the B field at both sides lowers the right-hand side term, facilitate KHI. So we have evidence for the solar wind entry via KH vortices, although it's the efficiency or impacts is still an open question. So the first evidence is that the formation of the cold and dense plasma layer in the flanks during northward IMF, which facilitates KHI. And the second evidence is the dawn-dusk asymmetry in the cold dense ions, which is hotter and denser in the downside. Then why the dawn-dusk asymmetry? Why is the dawn-dusk asymmetry related to the KH vortices? This is because the dawn flank here, favors the generation of KH waves under typical Parker spiral IMF, which is perpendicular to the K vector, so lowering right-hand side term, so easily generate KHI. But in the dusk side, it's parallel, so it's rather suppressed. And this is the MHD picture. But the kinetic picture also predict the dawn flank is more favorable place for KHI, because we already saw that the downside matrices is more turbulent, and which can act as the seed fluctuations for the KH waves for typical, again, the Parker spiral IMF. And the STEMS statistics of KHI occurrence also shows that strong preference toward the downside planks during the Parker spiral orientation. Okay, now the question is, how are the solar wind transport plasma mixing processed? The first answer is seems not. First answer is, is the diffusive transport through the turbulent, the decay of KH vortices, as you see in this movie. But if you see, I cannot rerun this movie. So if you see this in the middle of the movie, actually, you saw there is, let me see. Sorry. Like here, so you see, the formation of multiple X lines caused by the secondary, the tearing mode. So reconnection is also the important elements for the solar wind transport and the mixing here. Here it is. Now you see all those small flux ropes and also mixing of them. And the third element is the mode conversion from KH waves to the Kennedy Alpine waves. But we will take a closer look into the reconnection picture, which is called the vortex-induced reconnection. So what's interesting in this picture is that the KH flow, flow compresses the initially thick current sheet to electron scales, generating or triggering the reconnection. Then the electron scale flux ropes grow and merge with time and causing the plasma mixing. So this is called, again, vortex-induced reconnection. But KH vortices induce reconnection not only in the velocity shear plane, but also in the mid-latitude, where the KH vortex-driven 3D twist of a magnetic field shows a large magnetic shear and reconnected here and here. So this is called the mid-latitude reconnection. Sorry, here and here. So the efficiency of both the vortex-induced reconnection in the flow shear and the mid-latitude reconnection at the higher latitude has been estimated to be around the 10 to the 10 meter squared per sec. And you note that the plasma mixing layer rapidly expands after the onset of a vortex-induced reconnection. Then the next question is, then how deep is the solar wind transported? So this is again another the open question. But here is one example from MMS. So MMS was in the dusk world and tail it's around -22 in X and 10 RE in Y. The location and observed a series of cold dense plasmas. And the Nishino et al. Traced the source location, which is found to be dusk flank boundaries. So this event indicates the role of KH vortices in the earthward transport of cold dense ions of magnetic origin. I think this is the last slide for the KHI. So one of the global impact of KH vortices is vortex-induced field-aligned currents. So the KH vortices twist the magnetic field within the flux tubes, generating the field-aligned currents. And the sense of rotation at dawn and dusk consistent with the region 1 current. So we recently reported the supporting observations using MMS and cluster and FAST and GMX observations. So this is my the last slide, the summary. So because I actually covered the broad area, I will just let you lead it through. But let me emphasize that first this one. So as you see, FTEs and KH can coexist. They are not competing, or they can compete sometimes, but they are not always competing. They coexist or cooperate. It's the same as in other words, the reconnection and KHI can cooperate. And the two unknowns are here. So the roles and efficiency of KH vortices in the solar wind transport is still unknown. It's an open question. And similarly, how the FT is evolve and if affect the flank and tail dynamics is also unknown. So yes, this is it. Thank you very much.
All right, thanks, Joo, for great talk, compressing it. Just so everyone knows, all these plenary talks are uploaded to the wiki, so you can get more details later if you want. Students, do you want to? We'll take a question or two.
An incredible amount of material there, Joo. Very, very impressive. I have a question about the slide and the work that you've done regarding the ground signatures of flux transfer events, and in particular, the event in which there was, I don't think it shows on your slide, but it was in your paper, in which there was a relatively strong and almost dead steady IMF-BY. And yet these flux transfer events continually evolve or
Yes.
initiate, evolve another one later. Does anyone know why the magnetopause is so unstable for those conditions and exhibits these periodic structures?
So I think this is a really good question. So in this event, maybe I think you mentioned this event. Is it? Yeah, right. Yeah. So during this, so there is actually the IMF changes at some certain times here and here, I think, but like here and here. So it actually induces the global, the outward and inward motion of the magnetopause. But during history, I think there is, as you mentioned, there is not much variation in the upstream, the solar wind conditions, but still we see, as you said, we see the trend, the series of FTEs here. So the answer is I don't know, but I think this is very, this is really a good question that we have to answer. But I'd like to say one thing as, so we actually found that, on the simulations, we also found that reconnection is not, there is the primary reconnection line. There's also the component reconnection lines, and maybe the interaction, as I showed, like a flux rod, etc. So maybe interaction, the local interaction might be actually change the location for primary X line. So they may actually generate such a series of FTs. But again, yeah, this is a guess.
Can I ask a question?
Go ahead. One more question.
Oh, thank you for the very nice talk. So you mentioned about there's the connections and the Kelvin Helmholtz waves in the magnetosheaths, and should we care a lot about them because they seems not really impacting the magnetosphere? I mean, in terms of ionosphere perspective.
Could you say this one more time? What?
So you said that the connection can
Yeah.
happen everywhere,
Yeah.
even in the magnetosheaths, in size of electron scales, and what is their impact on the
Their impact.
ground?
Okay, that's also a good question. This is because the MMS is more like it's designed to see the small scales. So we really missing the information how those small scale the dynamics in the magnetosheaths affect to global the magnetosheaths, right? So that's why actually we actually have the string of the pearls configuration of MMS. So we might be answer your question after that. Yeah.
All right, let's thank our speaker one more time. And with that, we'll go into the break. Have fun the rest of the day, everyone.